the pure resolutions, right? And in the second hour we talk about homology tables and the rest of the proof, more or less, and then the open problems. Okay, so but before we do the pure resolutions, since this first construction was based on representation theory, we need to recall some things about representation theory of GLN and more precisely about Schur functors. Schur functors. And the reference for this is, for example, I think the book of Fulton Harris certainly contains everything that you will need, okay? So K is C, the complex numbers, and we take the vector space E as C to the N, and then we look at the group of GLE, which are just automorphisms over K, linear automorphism of E to E. So if you choose a basis in E, you can think of this as the group of n by n non-singular matrices. And then what we want to do, we fix a number D and we look at the default tensor product. And what we want to do, we want to describe how it decomposes as a GLE representation. So you see, when I have this E tensor D, this tensor power of E, I have two groups acting. Of course, I have the group GLE acting. Basically, G on V1 tensor VD is just GV1 tensor GVD. And then this extends uniquely to the linear action. So here G is in GL E, V1, VD are in E. But also the permutation group SD on D letters acts on this default tensor product just permuting the summands. Okay, so if I have sigma in here, sigma on V1 tensor VD equals V sigma 1 tensor V sigma D. Okay, and the main point that was observed already by Schur is that these two actions commute. Meaning G sigma is sigma G for every sigma in SD, G in GLE. It just follows from that formula, because it doesn't matter whether you first permute and then apply G everywhere, or first it's clear. So, in fact, we have those two group algebras, the group ring of SD, and then the span, so this is just a group ring of SD, and this is a span of all G tensor D, where G is in GLE, linear span, and this is called the Schur algebra. And in fact, Schur commutation theorem tells you that those two algebras are commutants of each other, that if C is the set of all endomorphisms of this that commute with all endomorphisms from B and vice versa. But okay, so this leads to a way of defining nice representations of GLE using the group ring. Okay, so what we'll do, we'll now let's recall a definition. The partition lambda of D is a sequence lambda 1, lambda s, bigger or equals 0, of non-negative integers and such that lambda 1 plus lambda s equals to d. Okay, and I will also I will draw a partition. This is so-called the Ferrars diagram. Of lambda, and I'll do it this way. Basically, a bunch of boxes like this. Okay, and the point is that I will have lambda 1, lambda 2. Number of boxes in the first row will be lambda 1, lambda 2, lambda 3. So, for example, this is 4, 3, 1. Yes.
In Schur's algebra, all G is equal, or?
Oh, that's right. All G is equal, and you take a linear span. So linear combinations of the things of the type this power of G. Okay, yeah. So I should probably write like this. It's a linear span. So it's an algebra. And those two algebras are their own commutants. But anyway, okay, so now what I can do, I will define certain GLE modules in the following way. So suppose I have partition lambda of D. Partition lambda of D. So that's how I'll denote it. Partition lambda of D. And now what I do, I fix a filling of Ferrars diagram with numbers, and I call this filling D with numbers 1 through D. Okay, without repetitions. So for example, I could take something like 1, 2, 3, or I could take 3, 1, 2. Doesn't matter, for D equals 3. And then for each such D, I'll define so-called Young idempotent. E of D equals as follows. So if I have my filling D, so this is one of the possible D's, I don't know, maybe this one. Let's take this. Maybe I take this, because that's what I wrote for the example. So each such diagram D defines two subgroups of our group SD. There will be the subgroup C of D, which is the all permutations preserving columns of D, and R of D are all permutations preserving rows of D. So for example, in this example, C of D will be just identity and the transposition of 1 and 2. And R of D will be identity and transposition of 1 and 3. Okay? So these are okay, and then this Young idempotent is defined in the following way. You take summation over all sigma in columns of D and tau in the row of D. And here you put sine tau, sigma tau. So example, if I have my 1, 3, 2, this is my D, then E of D is just 1 plus 1, 2, 1 minus 1, 3. Okay? Yeah, basically I could write it summation sigma in CD, summation sine tau in RD. Right? The same thing, so that's what I did here. Okay? So that's an element in the group ring of a permutation, or of this permutation group, sigma 1, 2, 3. And then the claim is, or the Young proved it, that there exists a scalar M such that actually integer that one of the m times e of d is an idempotent. So this means its square is equal to itself. Okay? So this is like a projection on a direct sum. And therefore we define S lambda E to be ED times E tensor D, where D is a diagram of shape lambda, like here. And notice here I should really write that it's SD. Why is it independent of D? Okay, because you see the point is, so I have a second diagram, say 3, 1, 2, that's my D prime, and my D was 1, 3, 2. Maybe let's make 3, 2, 1, and D prime is 1, 3, 2. Then you see I have a permutation sigma going from here to here, taking 1 to 3, 3 to 2, and 2 to 1. Okay, so then you can see directly that those basically E of D prime, so I have this permutation maybe, let's call it sigma. E of D prime, E tensor 3 is, I think, sigma E of D, sigma inverse E tensor 3. So it's isomorphic. They just differ by permuting this. So as GLE modules, as this sigma will just induce isomorphism of one to another. Okay? So sigma induces isomorphism of ED, E tensor 3 to ED prime, E tensor 3. Let's look at some examples, because this is the best in such a quick introduction. Examples. And by the way, unfortunately, my notation for diagrams probably is different than Fulton's, but okay, so let's take lambda to be a column of length D. Then, of course, E of D is just, you see, the partition preserving rows just consists of identity. Let's fill it maybe with 1, 2 through D, doesn't matter. So the group R of D is just identity group, and the group C of D are all the permutations. So you get summation sigma, sigma in SD. So therefore S lambda E will be just the symmetric tensors. Okay? So it will be SDE. These are symmetric tensors. And similarly, if I take D, lambda equals this, 1, 2, D, then E of D will be summation. And here now you see I have sign, because now the column subgroup will be just the identity, and the row subgroup will be the whole symmetric group. So I'll get this, tau in SD. So this is anti-symmetrization. So in this case, S lambda E is just wedge D of E, anti-symmetric tensors. And for all other partitions, you get kind of a mixture. Let me just give you one more example, just to because this probably everybody knows really. So let's just look at something like maybe something like this, I and J. So then let me just write this. So this is our lambda. So what is this lambda of E? Maybe let me just kind of explain. I will not really. So the point is that everything here, you see, first what I have to do, I should point out that since I anti-symmetrize first, okay, I start with anti-symmetrization on the right, whatever we'll get will be kind of anti-symmetric in the rows, okay? So this will be really wedge IE tensor, because whatever tensor we write will be anti-symmetric with respect to those coordinates. And then it turns out that if you have just two, it's like a symmetric power, so you have like SG minus 1E divided by some relations. And a more precise check will tell you that the relations are something I plus 1 E tensor S J minus 2 E, because I have a map of modules. You see, I always know that wedge I plus 1 E is embedded in wedge I E tensor E. Right, if I have a tensor, I don't know, V1 wedge 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 Vi plus 1, I can always take it to summation J equals 1 to I plus 1, and I skip 1. Okay, so this is a nice embedding of modules. So I look at this embedding, and then so I go from here to wedge IE tensor E tensor Sj minus 2E, and then you see what I can also multiply this into that. Okay, symmetric tensors you can multiply. So the co-kernel of this will be this S lambda E, for example, in such case. Okay, so these are examples of those Schur functors. And then there is a beautiful thing, one of the main things in representation theory, namely Weil dimension formula. So E is C to the n, and then lambda equals lambda 1 lambda n. That's right, I should point out that all the partitions we'll ever see will have at most n parts, because the row cannot be longer than n, because our space is n-dimensional. So if I have D bigger than n, you cannot anti-symmetrize. I mean, you get 0 when you anti-symmetrize. Okay, so we only get partitions that I write lambda 1 through lambda n. Yeah, so let's just write otherwise S lambda E is equal to 0. And then dimension S lambda E equals product over all n J minus I. Okay, so there's Weil dimension formula, which is actually true. Usually this is a way to write in representation theory sum over positive roots, lambda plus rho alpha divided by rho alpha, where rho is 1/2 of the sum of positive roots. Okay, so in our case, rho will be n minus 1, n minus 2, 1, 0 for the group GLN. But so this is the nice formula, and well, if you work it out a little later, you will see that this multiplicative form already, you can see it's maybe similar to those Herzog-Kuhl equations, the solutions that we had of the Herzog-Kuhl equations. Okay. Okay, I should point out, yeah, maybe let me give you another way of counting the dimension. Yeah, if I have my first diagram, another way of counting dimension by standard tableaus. maybe it will, sometimes it's useful to see things. So if I have my diagram, so this is lambda 1, lambda 2, lambda 3, then you see I can also kind of read this partition by rows, and this is so-called conjugate partition. So if lambda equals 4, 3, 1, as we have here, then the conjugate partition is 3, 2, 2, 1. And so then, because of this anti-symmetrizing, this S lambda E, it's really, you can write it as lambda 1 prime E, tensor product of the axial powers lambda S prime E, and divided by some relations, so-called shuffling relations. You can look in Fulton and Harris what they are. Okay, I will not exhibit them here. But the point is now, you see, that this gives you the following thing. That now choose a basis in E, and let's denote it, say, E1, En. Okay? Then, and let's define the following thing. A semi-standard tableau of shape lambda on numbers 1, 2, up to n is a filling of lambda with numbers 1 through n such that so I have my lambda and I fill it in the following way, with 1 through n, with possible repetitions. Maybe let's write with possible repetitions. Such that, let me just write it, it's strictly increasing in rows and weakly increasing in columns. Okay? Maybe let's call this thing T. And what I just want to say is this, that if I have such tableau T, then I can associate to it the element T in the brackets in S lambda E. Because you see, if I have my T is T11, T12, T13 up to T1, comma lambda 1 prime, T21, T22, etc., T2 lambda 2 prime, etc., in some filling of my tableau, then of course what I can do, I can take in the tensor product of those axial powers, I can take the tensor E T11 wedge, E T12 wedge, 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 E T1 lambda 1 prime, tensor ET21 wedge ET22 wedge wedge ET2 lambda 2 prime, etc. And I can define T to be the coset. T is the coset of this tensor. So you see, then it will be clear why those things should satisfy this condition, that they should be increasing, because they are antisymmetric in rows. I can always rearrange. Of course, they don't have to, if I'm just here, they don't have to satisfy anything in the columns. However, after I divide by those relations, the semi-standard tableaus will form a basis. Okay, so the theorem that you can again read in Fulton and Harris is that the semi-standard tableaus, the tensors corresponding to semi-standard tableaus, so theorem going back to also Young at least, semi-standard tableaus of shape lambda filled with 1, 2, n are form a basis of this S lambda E. So that's some kind of a way of viewing this Schur functor. It actually, maybe this will not be that important in what follows. Okay, but so I just need one more formula and then we can construct the pure resolutions. So you see, the point is also that it's well known since also probably Hermann Weil, that the group GLE in characteristic 0 over C, GLE is linearly reductive. So what this means, that every representation decomposes to a direct sum of irreducible ones. And of course I did not say the most important thing. Those S lambda E are the irreducible, all irreducible, well, polynomial representations. So you get every irreducible representation of this S lambda E when you maybe multiply by some power of negative power of determinant. But so for our purposes these are all irreducible. So this means the fact that the group is linearly reductive means that any representation, and let me just write polynomial representation of GLE decomposes to S lambda E's. Okay, so that's really why one takes all this trouble to define those representations. So in particular now, we have something, we could ask if I have S lambda E and I take this, say, T-sec 0 symmetric power, how does it decompose? It has to decompose to the direct sum of Schur functors. And it turns out that this has a beautiful decomposition, namely, each representation will occur at most once, so it will be multiplicity free. And we sum over all partitions such that lambda is contained in mu, in the sense that the first diagram of mu is bigger, then mu divided by lambda, the axis is t, so it means I added t boxes. Okay, and there is something like this, that mu divided by lambda is a vertical strip. I'll give you examples in a moment so it become clear, i.e. no two boxes are added in one row. So the best way to do it is to do it by an example. Let's take 3, 1, tensor S2. And what I do, I just will draw the partitions, okay, that will occur. So 3, 1 is this partition. And now you see I need to add to it 2 boxes in such a way that it's a vertical strip. Okay, so how many ways? Well, I can add them here, maybe like this. Okay, then maybe I can add 1 box here, 1 box here. Then I can add 1 box here and 1 box here, and this uses all possible ways to have 1 box added here. So now I don't have the right to, so then I have this guy. I have this guy, and now I'm done. There's no other way. So this means that this is S51 plus S42 plus S411 plus S33 plus S321. Okay, and it's very important that this is multiplicity free. Okay, So this is really the formula we need, because with this we can construct the pure resolutions. So the idea was that basically so we have A, which is C x1 xn, and we just think of this as being the symmetric algebra on the vector space E. Okay, so this decomposes into the symmetric powers. So this homogeneous component, almost by definition, is just our Schur functor SD0000. Okay. Okay. So what will we do now? So actually, we'll construct this acyclic complex such that the only free modules we'll ever see will be the modules of type S lambda E tensor EA. Okay. So this will be the modules that we'll use. So this is a free module over A. But we'll construct this resolution in such a way that the maps are equivariant. So in order to understand the maps, let's do the following construction. So we can okay, so we construct equivariant maps between these three modules. Namely, so choose two partitions, mu and lambda, and such that mu is in lambda tensor SDE. So mu was created from lambda by adding d boxes according to those rules. Okay, maybe we can do t even. Okay, with t. Then we construct equivariant map of three modules, A modules, from S mu E tensor A, and I should write graded, into S lambda E tensor A, and let's call this map phi mu lambda, as follows. So we construct this map as follows. So you know, this is a map of three modules, right? So what do I need to do? I need to tell you what are the images on the generators, right? So what I need to do in order to construct phi mu lambda, we need to define the map from S mu E into S lambda E tensor STE. Right? Because it has to be map of degree t, and the tth component of A is the tth symmetric power. But you see now, the point is, by this Pieri formula, this representation occurs in this tensor product exactly once. Okay? So this means that there is a unique map up to non-zero scalar that embeds this, which is equivariant, GLE equivariant, that embeds this into that. Okay? So that's what we take. So this map then will be defined up to a non-zero complex number. These are very complicated maps. Okay? But representation theory tells you that such a map exists and is defined up to a non-zero complex scalar. So this is equivariant embedding. Okay, so this phi mu lambda defined up to non-zero complex number. But we don't care, because you know we can. Okay, So now we can start our construction, and again the best thing is to do it on the example. So I'll do an example, and you will be able to see. I will not actually exactly prove that the complex that we get is acyclic, but you will see from representation theory that it's very likely to be acyclic. Then one just needs to fill some details to prove it, and from example then it will be clear what the complex is. Okay, so I'll abbreviation. Well, if I just write lambda, it's really my S lambda E tensor A. Okay? So let's start with the partition 431. I take n equals to 4 here, so that's example. And I construct some acyclic complex, which will be one of those pure complexes, and you will see why it works. That's right. And let's suppose that the first degree shift will be 2. So what I'll do, we start with the following map, where I added, I put kind of ones into here because that's the first map. So I start with this map. So this is really my map 5, 6, 3, 1 and going to 4, 3, 1. Okay, this is a map of degree 2. Okay, and you see what I want to do now. I would like to resolve this map. So this is a matrix, and I would really like to find syzygies of that matrix. So let's think. Remember, what really we have here, it's an infinite direct sum of all partitions, which you get from here by adding vertical strip of arbitrary length. Right? Because this is this tensor A, tensor all symmetric powers. So you'll get, you know, all the partitions that are like this, I don't know, and going arbitrary high. Okay. So now I would like to see which partitions would be in the kernel of that map going into here. Okay. This will be, of course, the partitions that, for example, representations that occur here but do not occur here. Okay. So such representations will correspond to the partitions that you can obtain from here by adding a vertical strip, but you cannot obtain them from here by adding a vertical strip. And if you think about it for a minute, you will see that among all partitions, such that you get them from vertical strip from this one, but you cannot get them from this one, there's one which is the smallest one, which will be this one. Well, let me draw it here. Because clearly I obtained it by adding a vertical strip, but from here you see it's not a vertical strip. So here I have a violation. It's not in here. So I'm sure representation theory tells me, those maps are very complicated, but representation theory tells me that the composition of those two maps of the type phi is 0. Because this guy does not occur here. They're just maps are equivariant, so they have to take representation of a given type to a representation of the same type. Okay? Okay. So what do I do next? Now I need a partition which can be obtained from that one by adding a vertical strip, but it cannot be obtained from that one by adding a vertical strip. This will be in the kernel. Well, again, if you look at everything that you can obtain from this one by adding a vertical strip, there's the smallest one that has this property. If I add the 3 boxes here, I'll have a violation here. Okay? So I take this map. So, and you see, so again, I'm sure, without just by representation theory, that this composition is 0, because that guy does not occur in this module, because it's not by adding a vertical strip. Okay, and then I continue. The last thing is, since n equals 4, the process will stop here. So just those numbers that are right here do not have any meaning. It just kind of tells you at which stage the partition was obtained. So now I have another, the same trick. I mean, the guy which is in this 1 times vertical strip, but it's not in this 1 times vertical strip, there will be the smallest guy like that. Okay? So I got a complex. Certainly I got a complex of those modules. Okay? But now we would like to see why is this complex acyclic. Notice also the complex is pure, because the degree shifts is 0, 2, then another 2, 4, 7, 9. It's pure because the maps were homogeneous. So now I need to convince you that this is an acyclic complex. If I can show you that it's an acyclic complex, we constructed a pure resolution, and then we see what happens to do the how do we get the general case? Why the complex is acyclic? I will not give you the absolute proof, but I'll convince you that it's true. Namely, what we'll do, remember, each of those is really infinite family of partitions, right? Such that, well, each partition here times all possible additions, so we get a vertical strip. So what I'll show to you is like this, that we have a cancellation, that every partition that you ever see, for example here, will either occur here also or occur here. They will divide into 2 parts. Part that occurs here, so they'll cancel out, and parts will occur here. Okay? So then, well, one still will need, really would like to be precise, one would have to show that really this map will induce a non-zero map on those representations, which can be in very high degree, but it actually can be done. So let me just show you combinatorially. Okay. So let's look at the second. So I concentrate on this module, and I show to you that every representation that occurs in this module either occurs in this module or in that module, and it doesn't occur in both. Okay? So okay, so now I take, so you see, if I take vertical strips, partitions that I obtain by adding a vertical strips, I have 2 possibilities. Either I could have partition like that, which contains this box, or I could have a partition like that, that does not contain that box. Okay, so the partitions occurring in this module divide into 2 disjoint classes, those that contain that box and those that do not contain that box. Okay, and the point is now, this partition, if it doesn't contain this box, it occurs in S431 tensor A, because you see, then I could just kind of count those 2 boxes. Together with those 2 boxes, it will form a vertical strip. Okay? On the other hand, if the partition occurs here, then it contains this 651, so then it's in S651E tensor A, because I forget those 2 boxes. Now these are my 2 boxes numbered with 2, and of course the rest is still a vertical strip. Okay, so that's the point. So all vertical strips in here either contain this box, then they also occur here, or they do not contain that box, and then they occur there. Okay, so if you believe that, you know, the map is kind of generic enough, scalars are non-zero, and that's exactly what one can prove happens, there occurs a cancellation. So you see, so basically there's no homology here, because either something goes to something non-zero here, or if it doesn't occur here, it comes from here. So this is really indication that the complex does not have homology there. And of course the same is here. Here we divide according to whether they contain this box or not contain that box, and they either go there or there. Here we divide according to whether they contain this box, etc. And this map is just here, just it will be injective. Okay, so this is the example, and again, I did not prove this fact, but it's not that difficult to prove that this complex indeed is acyclic. There are actually two proofs. Okay, this is the way we did it with Eisenbach and Floistad, is to use some representation theory and do it by induction on N using the projective space and some sheaves. But then the Stephen, Sam, and me, we actually showed that even direct calculation can be made. Okay, that you can directly show that this map will send all non-zero partitions that you need to non-zero partitions. Okay, but this is just an example. So now how do I create the arbitrary shifts? But that, you see, now it's very easy, because well, let's see, if I have D, which is D0, D1, D2, up to Dn, then I define EI to be Di minus Di minus 1. Okay? So this is really the degree of that map. How many boxes I add at the I stage. So what do we do? Let me just draw you the partition. Basically what I need to do, I need to draw this partition, and then you will see that the same construction will give you the same degrees. This is the degrees that you want. Basically we draw the following partition. So here I do E2 minus 1 boxes, E3 minus 1 boxes, etc. up to En minus 1 boxes. Okay, such shape. Then you see the first addition of E1, I don't care. I can just add to the first column as many boxes as I want. And then you see here, if I do the same construction, I'll have degree E2. Here I have degree E3, because it's always by one more, degree 4, and so on. So by choosing the initial partition, appropriately, we get arbitrary shifts. Okay? So that's, one can, there are many interesting things one can see about this construction. For example, what is a co-kernel? Okay, what is the module which is a co-kernel? Let me just write it out. So let's call this complex F of D. And this is, maybe I will not talk about co-kernel. Let me do some examples, because, yes, let me do some examples, because I probably will take 5 minutes. Because some of those examples are very familiar to you. Let's take D to be 0, 1, 2, up to N. So what do we get? So what is our partition? All our numbers E are equal to 1. So you see the initial partition is empty. No boxes. Okay? So what do we get? We get just A. But then, so let me just say empty diagram. Then I add one box. But then you see, I have to add, so this would be the box that I would call 1, then 1, 2, 1, 2, 3, etc. So really my complex is A, E tensor A, wedge 2E, the minus 1 here, wedge 2E tensor A minus 2, wedge NE tensor A minus N. So this is just a Koszul complex. on the variables. Okay, let me show you another example. Let's start with some m plus 1 up to m plus n, I guess. Okay, so then I start with m, okay, then I add 1. That's not what I wanted. Oh no, sorry. M. No, I want to, I want to 0 m plus n minus 1. No, sorry, that's how I want to do it. So then you see what happens again, the initial partition is empty. But here I get m boxes, which would be filled with 1 according to our rule. And then I get 1, 1, 1, 1, 1, and then 1 violation 2. I mean 1, and then I would get 1, 1, 1, 1, 1, 2, 3, etc. up to 1, 1, 1, 1, 1, 2 up to n. Right? So what do I get? I get A. Here I get SME tensor A minus m. So basically what you get the resolution of the mth power of the maximal ideal. And well, I don't know, if you write them in terms of representation theory, you know that these are exactly those Hooke-Schur functors. So this would be, or S, what would that be? SM1 E tensor A minus m minus 1, SM2 1 E tensor A minus m minus 2, etc. So I'm sure some of you are familiar with this resolution, mainly, but maybe by different names. Okay, so this is a resolution of A mod, well, m to the m. I choose the letters in a rather unfortunate way. So let me still show you some examples about what are the dimensions of the modules involved. Because remember now, yes?
For the monomial case using.
Yes, because the monomial ideal is the power of maximal ideal is a monomial ideal, right? Well, this is ideal generated by all monomials of degree m.
Yeah. In this case,
Yeah.
that's right. But I mean, general case, generated by monomials.
Yes, this is not pure. It's never pure.
Okay.
Almost never pure. Yeah. Actually, no. For n equals to 2, actually, Boij and Soderberg constructed all pure resolutions using some modules related to monomials, not ideal generated by monomials. But let me show you some examples, very small examples for n equals 3. So let's look at the following degree sequence: 0, 1, d equals 0, 1, 3, 4. So you see, this is the shifts are 1 to 1. Okay, so what do we get? Let me just write my sequence. And if you count by Val character dimension formula the dimensions, you'll get 3, 6, 6, 3. N equals 3 here. So you see, this is a Betti diagram. 3, 6, 6, 3. But remember, on the other hand, we constructed 2, 4, 4, 2. During the previous lecture. So we know now that on this extremal ray, every integer bigger than 1 can be covered. Bigger than having something bigger than 1 here can be covered, but 1 cannot be covered because we proved that this doesn't exist. So this is an example, you know, that those two pure resolutions somehow told us that on this ray there is just one empty spot and everything else can be covered. And in fact, this family, in the paper with Eisenbach and Floystad, we construct another family of pure resolutions with arbitrary shifts. So these are really module support in determinantal varieties, and that, okay, but in some cases, well, I come back to this maybe at the end. In some cases, for example, it could happen that both of those are, for example, even or divided by 10. So even those two examples do not tell you that you cover the whole extremal array. And you know, let me just take another random example just to show you what you get in maybe slightly more complicated case. For example, let's take 0358. So you see when you get S3 to 0, then S6 to 0, S640, S643, and you calculate the dimensions, you get 15, 60, 60, 15. So you get, you see, very high multiple of the integer vector. Okay, so that's a typical situation that this construction and actually any other that is known typically produces quite high multiples of the minimal integer vector on the extremal array. You see, so we don't know from 1 to 14. We don't know whether, well, okay, maybe for this array, if one would, you know, look more closely, one will find, but at least this construction doesn't tell you anything about what happens from 1 to 14. Okay, so actually this is one of the typical open problems, to look at extremal arrays and see, you know, which points you can cover by a module. Okay, so now it's a good point to take a short break, and then I continue.
Okay, let's continue after 10 minutes.
10-minute break, yeah.